Alright, so in today's tutorial video, we want to look at statistical methods for analyzing one sample data in SPSS, okay? And before we proceed, I will urge you to kindly take a look at my previous tutorial video on the flowchart for classifying data, okay? Because in that video tutorial, I have explained and illustrated the data structure for one sample data, which will help you to catch up with everything that I'm going to illustrate or do in today's tutorial video. Okay, so now let's get started. Now, generally, anytime you have one sample data, there are two statistical techniques you can actually use to analyze such a data. We have the parametric test and we also have the non-parametric test. Parametric tests are statistical tests for population parameters such as the mean, that is based on the assumption that the population from which the samples are selected will follow a normal distribution. The non-parametric tests, on the other hand, are statistical tests for population parameters such as the median, that is not based on the assumption that the population from which the samples are selected will follow a normal distribution. Okay, so the type of parametric test that we often use in analyzing one sample data is called a t-test or the one sample t-test. And the non-parametric test we often use in analyzing one sample data is called a sign test or the quantile test. So let's take a look at the parametric test one sample data, which is the one sample t-test. The one sample t-test is a statistical hypothesis test used to determine whether an unknown population mean is different from a specific value. For example, we might want to know if the mean waiting time in a doctor's office is greater than 1 hour, or if the mean growth of roses is 4 inches or more after 2 weeks of treatment with a certain fertilizer. There are some assumptions which must be satisfied before we make use of this test. One of the assumptions is that the data must be continuous, and the other one is that the data must be normally distributed. Okay, let's take a look at the non-parametric test for one sample data, which is the sign or the quantile test. So the sign test is a statistical hypothesis test used to determine whether an unknown population median is different from a specific value. For example, we might want to know if the median waiting time in a doctor's office is greater than 1 hour, or if the median growth of roses is 4 inches or more after 2 weeks of treatment with a certain fertilizer. There are some conditions which must be satisfied before we make use of this test. One of the conditions is that the data must be continuous, and the other one is that the data must not be normally distributed. Okay, so now let's take an example. Using the iris dataset, as a researcher, you wish to test whether the average length of the sepal from the iris dataset is different from 6 centimeters. Perform statistical analysis for this data. Okay, so before we start with the analysis, let's take a look at the iris dataset. So this is the iris dataset, and this is a clean data. Okay, before you analyze any data, you have to first of all clean or prepare it. Okay, so we have assumed we already cleaned the data, so this is a clean data, even though we may have to do some data manipulation before we start with our main analysis. Okay, so I'm going to leave this data file in the description of the video so that you can download it. Okay, alright, so the problem at hand is that we want to find out if the average length of the sepal, right, is different from 6 centimeters. Now this is the variable for the sepal length. If you just make use of this whole variable, right, in your analysis in performing the t-test or the quantile test, you may end up doing a wrong thing or providing a wrong inference, because you have to first of all note that the sepal length was taken for 3 different groups of the species. We have one for Setosa, we have one for Vesicular, and we also have another one for Vesicular. So before you start with analysis in your data manipulation, first of all, you have to filter the sepal length for Setosa. You have to do same for Vesicular and do same for Vesicular, and then perform a t-test or quantile test on each one of them. Okay, so that's what we're going to do. So let's jump into SPSS and import the data set and get started. First of all, let's close this. Okay, save. So now I can go back to SPSS. I have it in the same folder. So this is the folder where I have my data file, and if you don't close it and you try to import it, you may have some challenges. So it's good to always close the CSV file. Yes. Alright, so now we want to import our data set, so I'm going to use this icon, that's the open data document. Right, I'm going to click on this, which will send me to the folder where I have my data file. So yours may be different, you just have to navigate and check the folder where you have your data file. Okay, So I have mine in here. Then I'll go to the files of type, and I'm going to choose all files. So let's scroll down. I'm going to choose all files. Right, so I have my clean data.csv. I'm going to click on this and then open to basically view my data set. Okay, so I think we have some command window which we have to follow before we can finally view our data set. So in here we can leave this session as default and click on next. Right, now in here leave this side as default. Variable names included at the top of your file. If you look at the preview of your data set, you can see that the first row is made up of variable names, right? So we can check yes and proceed with next. Right, at this session you can leave everything as default and click on next. The same applies here, leave everything as default and click on next. Also you can leave everything as default and click on next. Let's leave everything as default and click on finish to basically view our data set. Okay, so once you import your data set, you also have an output window, right, or your result window where you can see most of the results from your analysis. Okay, we'll be making use of this very soon. Let's go back to our window editor. Alright, so this is the imported data. Right, we can also, this is the data view side. We can also check the variable view to get some information with regards to the variables. So the separ length, separ width, petal length, petal width, they are all numeric, right? And species is string. Okay, so in our data manipulation, we are supposed to basically assign values to the labels of the species. Okay, so we have to do some encoding. Even though we have the measurement to be nominal, we are supposed to basically assign some values or convert this variable from string to some numeric, okay, by assigning values to the labels of the species. So let's quickly do that. So let's go back to data view and scroll up. So let's go to transform, right, and let's go to automatic recode. So in here I want to basically assign some values to the labels of the species. So let's click on species and drop it inside this box. Right, so we don't want to override the previous species that we have in our data set. Okay, so we want to give it a new name. So let's give it a new name. Let's say species 1. Okay, and let's add a new name. Let's leave everything as default and click on OK to proceed. Okay, so now if you look at the result window, we can see that these are the old value. The new value is that we have 1 assigned to Setosa. We also have 2 assigned to Vesicular, and we have 3 assigned to Virginica. Okay, let's go back to our window editor. Yeah, so now if you check this, if I click on the value labels, you see that it will be changing for this new variable species 1, but the previous one doesn't change because it's string. Now we have assigned some value to the labels. So 1 has been assigned to Setosa. If you scroll down, you see that 2 has been assigned to Vesicular, and we have 3 being assigned to Virginica. So I think we are good to go. Alright, so let me use this. Okay, so we don't need this variable anymore, so I can just right click on this and clear. Alright, so now that we have this done, the next thing that we want to do is to basically filter the separ length for each of the labels that we have here, right, before we can start with our main analysis. So we're going to filter the separ length for Setosa, do same for Virginica and Vesicular, right? So let's get started. Let's go to data, scroll down to select cases, right, and I think we should have some window. Yeah, so in this we are going to use the if condition. Let's check this and click on this. Alright, so let's drop this variable inside the box, right, and we want to pick the label Setosa, which was assigned 1, right? So now we can go back and click continue. Now we don't want to filter out the unselected cases, rather, but we want to copy the selected cases to a new data set. So let's check this and give it a new name. Let's say gene1 underscore XL, yeah. So that's the group 1 of the separ length, which is made up of Setosa, right? So let's click on OK to basically proceed. Alright, so let's check that data. So this is the G1 underscore SL, right? Group 1 of sepal length. And if you scroll down, you see that we have only Setosa. We don't have the other labels or the species, right? Okay, we don't have the other ones. So we are interested in only sepal length, so we can just right click and highlight these ones, right click on them and clear. Right. Okay, so now we have the sepal length for Setosa. So we are good to go. Now let's go back to our original data set and filter that of Vesicular. So this is our original data set. Let's use the recent dialog icon. Go back to select, oh sorry, select cases. Let's check this off. Go back to recent dialogs. Yeah, select cases. Let's click on the if and change 1 to 2, meaning we are interested in Vesicular, and click on continue. And the output now, we are going to change this to G2 underscore SL, which is the group 2 of the sepal line, which is made up of Vesicular. Right, so we can click on OK to view that data. So let's check it out. Okay, so here we go. So this is the data set for Vesicular, right? If you scroll down, we have, yeah, I think 50 observations. This is only made up of Vesicular, but we are not interested in these variables, so let's highlight them, right click on them and clear, right, so that we get the sepal length for Vesicular. Now let's do same for Virginica. So let's go back to our original data set. This is our original data set, so let's use the recent dialogs icon, select cases. Let's check the if and change 2 to 3. Alright, so we are interested in Virginica data. Click on continue, change the name, output name to group 3 of sepal length, right, which is made up of Virginica. So you can click on OK to proceed. Did I click on OK? Okay, so this one is made up of only Virginica, right? Let's scroll down and see. Scroll down. So we have only 49 observations, but we are not interested in some variables. Let's highlight them. So let's highlight these 3, right click on them and clear. Okay, so we get the sepal length for Virginica. Okay, so now that we have filtered our data set for the sepal length, we can then proceed and do some exploratory data analysis on each one of them so that we can get to know whether we are going to make use of the t-test or the quantile test. Okay, if you have not watched my previous tutorial video on exploratory data analysis in SPSS, you can kindly go check that one out before you jump into this. Okay, so in our exploratory data analysis, let's start with the first data, which is the sepal length for Setosa. Okay, so let's check the analyze, go to Descriptive Statistics, scroll down to explore. Okay, alright, so let's drop this sepal length inside the dependent list box, right? So yep, then let's check statistics. What do we have to do? We don't have to do much here. Let's go to plot. Yes, so let's uncheck this and check that of histogram, and the box plot, let's leave it as that. Normality plot with test, let's check that one. And okay, so let's click on continue. Let's look at the options. We don't have to do much here, so you can proceed and click on OK to view our result. So let's go to our output or the result window. Okay, alright, so let's scroll down. I think it's still compiling. Okay, so let's scroll down. It's still running. Okay, once it's done, we are going to see the result. Okay, yeah, so here we go. So we have some descriptive statistics, right? So these are some of the things you're supposed to talk about, right? Some descriptive summary you're supposed to talk about before you start with your main analysis, okay? So it's very important you pay close attention to this. So from the sepal length for Setosa, we have 49 of them, and we have the mean value around 5 centimeters, right, which we have it here. So this is where most of the data points are being clustered. The peak of the data is around 5 centimeters. We also have the median value, which is 5 centimeters, meaning that if you have to divide our data set into two, we have 50% of the values that will lie below 5 centimeters and 50% of the values will lie above 5 centimeters, okay? We can also take into consideration the variability in our data set by checking that of variance and standard deviation, okay? The variance is always measured in square units, but standard deviation is measured in linear units, so it's always good to interpret that of the standard deviation. Then we also have information with regards to the minimum and maximum value. Once we subtract the minimum from the maximum, we get the range, and the range basically tells us the dispersion, the overall dispersion of values in the data set, okay? Then we also have information with regards to the interquartile range, which is obtained by subtracting the first quartile from the third quartile, okay? Then we also have to get information with regard to skewness and ketosis. Skewness and ketosis basically help us to know the shape of our distribution, okay? Skewness is basically let's say, is a measure that describes the degree and direction of departure from symmetry, right? We know that a distribution is said to be symmetric if it has the same shape on either side of the center value. So once a distribution is having an equal shape on either side of the center value, then it means that it is skewed. So according to literature, if the skewness coefficient is within the range of minus 0.5 and plus 0.5, then it means that the distribution is said to be nearly symmetric. So what we have here, it means that the data for sepal length, right, the data for sepal length for the Setosa is symmetric, right, from the coefficient that we have here. Then with ketosis, we normally interpret that of the SS ketosis. The SS ketosis is basically used in comparing the ketosis coefficient with that of the normal distribution, right? It is obtained by subtracting 3 from the ketosis coefficient. Now, if the SS ketosis is less than 0, as in our case, then it means that we have a plateautic distribution, which means that the peakiness in the curve is flat and spread out, or the tail of the distribution is flat and spread out, right? But if the SS ketosis is greater than 0, then it means that we have a leptokurtic distribution, which means that the peakiness in the curve is high and thin, or the tail in the curve is high and thin, right? And if the SS ketosis is approximately 0, then it means that we have a mesokurtic distribution, which means that the peakiness in the curve is normally in shape. So what we have here tells us that we have a plateautic distribution, okay? So these are some of the descriptive summaries you can talk about, and let's look at other tests. We also have information with regards to the test of normality, and we are going to interpret that of the Shapiro-Wilk test instead of the Kolmogorov-Smirnov test. The modification of this test is given by the Anderson-Darling test, okay? But we are going to interpret that of the Shapiro-Wilk test, which is one of the main tests for normality. Here we have the significance value, or the p-value, to be 0.325. If you are to compare this to the threshold value or the alpha value of 0.01 or 0.05, it means that we are failing to reject the null hypothesis. We only reject the null hypothesis. The null hypothesis of this test states that the data is normally distributed. We only reject the null hypothesis if this p-value or significance value is less than the alpha level of significance, or the threshold value. But because this one is greater than the alpha level of significance, we can't reject the null hypothesis, but we have to fail to reject the null hypothesis and conclude that the data of the sepal length for Setosa is normally distributed, and therefore making use of the t-test is required, okay? Now let's scroll down and see. We also have information with regards to the histogram plot of the sepal length for Setosa. And if you look at this is a typical example that we have a plateautic distribution, which means that the peakiness in the curve is flat and spread out, right? And let's scroll down to see other exploratory information. We also have the QQ-Plot, or the normal quantile plot, which basically draws the correlation between a given sample and the normal distribution, such that if the data is approximately normal, what you are going to observe that the plot will closely resemble a straight line sloping upward to the right, as in this case. So with this, we can say that the data or the sample length for Setosa is normally distributed, and therefore making use of the t-test is required. This is basically confirming to the Shapiro-Wilk test result. Okay, let's scroll down to see other exploratory information. We also have information with regards to the box plot. Now the box plot basically is a way of displaying, let's say, the distribution of the data based on the 5-number summary. Okay, so let me scroll down. The first item can be indicated at this side, right, which is the minimum value. We can also get the first quartile or the 25th percentile at this side. The median value is given at this middle line, right, which is heading pointing towards 5 centimeters. We can also look at the third quartile or the 75th percentile at this point, right, and the maximum value is given at this point. Aside information with regards to the 5-number summary, the box plot also helps us to know the shape of our distribution. If you look at the distance from the maximum value to the third quartile, and if you look at the distance from the minimum value to the first quartile, you can see that this side seems to be a little bit longer compared to this side, right? Assuming if you are using this middle box as your center value, then we can say that this is nearly symmetric. Also, if you have to consider the area at the upper half of the median and compare the area at the lower half of the median, they are almost the same. So this is an indication that the shape of the distribution is nearly symmetric, right? Now let's check that of the respiratory analysis for the vesicular data. So let's go back to the data for vesiculars. Yeah, so this is the sepal length for vesicular, right? So you can also do some respiratory analysis on this to know the kind of statistical test you are supposed to make use of. So let's go to analyze, scroll down to descriptive statistics, and let's choose explore. Right, so we are going to drop this sepal length variable inside this dependent list box. So let's do that, and let's go to plot. Right, let's uncheck this and check that of the histogram, and let's check that of the normality plot with test. Let's click on continue to proceed. Alright, so I think we are good to go, so we can click on OK to view the result. Let's go back to our result window. Alright, so let's scroll up and see, scroll up. So this is gene2 underscore SL, which is the group 2 of the sepal length, which is made up of vesicular. So yeah, the number of counts, we have 50 of them. We also have the mean value getting around 6 centimeters. Right, we also have information with regards to the variability in our data set, the variance and standard deviation. We also have information with regards to the range, minimum, maximum, and the shape of the distribution. Skewness is around 0.105, which is within the range of minus 0.5 and plus 0.5. So we can say that the shape of this distribution is nearly symmetric, right? And if you look at the ketosis, it's less than 0, so we have a plateautic distribution, which basically means that the peakiness in the curve is flat and spread out. Okay, now let's look at the Shapiro-Wilk test result. So if you have to compare this significance value or p-value to the threshold value or the alpha level of significance of 0.01 or 0.05, it means that you are failing to reject the null hypothesis and conclude that the data of the sepal length for vesicular is normally distributed, and therefore making use of the t-test is required. Okay, let's scroll down to see more exploratory information. Let's look at the histogram plot. So this is an example, an indication that we have a plateautic distribution. Let's scroll down to the QQ-Plot. So you can see that the points are on the straight line, which basically resemble a straight line sloping upward to the right. So we can see that this is confirming to the Shapiro-Wilk test that the data of the sepal length for vesicular is normally distributed, and therefore making use of the t-test is required. Let's scroll down and see the box plot. So if you look at the box plot for this, you can see the distance from the maximum value to the third quartile, and the distance from the minimum value to the first quartile. Assuming if you are using this box as the middle value, you can see that they are almost the same, right? So this can be said to be nearly symmetric. Also, if you consider the area at the upper half of the median is a little bit larger compared to the area at the lower half of the median. So this is also, sorry for that. This is also an indication that the data of the sepal length, that the shape of the distribution for vesicular, right, is also normally distributed or nearly symmetric. So let's check that of the Virginica data. Let's go to the Virginica data and do some experimental analysis on them. So we are now we can now confirm that the sepal length of the setosa and the sepal length of the vesicular, we can make use of the t-test, right, from the experimental analysis that we have. Let's check that of the Virginica. Analyze, go to Descriptive Statistics, scroll down to Explore. So let's drop this sepal length inside this box. Alright, and let's look at the options. Plot. Let's check the plot instead. Let's uncheck this and check that of the histogram. And let's check the normality plot with test and click on continue. So we can click on OK to proceed. So let's go back to our result window. Okay, so this is the group 3 of the sepal length, which is made up of Virginica. We have 49 observations of them. The mean value is around 6.6 centimeters. We can also get information with regards to the variability in our data set, standard deviation value. We also have the minimum, maximum, as well as the range. Then let's look at the skewness coefficient, which is within the range of minus 0.5 and plus 0.5. So we can say that the distribution of the sepal length for Virginica is also nearly symmetric, right? And let's look at the ketosis coefficient. SS ketosis is basically greater than 0, which means that we have a leptoketic distribution, right? Meaning the peakness in the curve is higher than 10, or the taste of the distribution seems to be higher than 10, okay? Okay, so let's scroll down and see the normality test. The Shapiro-Wilk test, the significance value is 0.253, which is greater than the threshold value of 0.05 or 0.01. So basically we are failing to reject the null hypothesis and conclude that the data or the sepal length of the Virginica is normally distributed, and therefore making use of the t-test is required. Okay, let's scroll down to the histogram. So this is the shape of the histogram, which we had to be leptoketic. Let's scroll down to the QQ-Plot. So we can see that in here some of the points seems to deviate from the straight line, but we can see that the majority of the lines are on the straight line sloping upward to the right. So this is an indication that the sepal length of the Virginica is normally distributed, and therefore making use of the t-test is required. Okay, let's scroll down to the box plot. So in here we have some extreme values. Okay, having an extreme value does not necessarily mean that they are outliers. You have to be very careful when you're dealing with outliers. Okay, so in here we can see that the shape of the distribution, if you look at the distance from the maximum to the third quartile, if you compare that to the minimum to the first quartile, they're almost the same if you have to consider this box as a middle value. So we can see that they are almost nearly symmetric, even though the area on the upper half of the median seems to be larger compared to the area on the lower half of the median. Okay, so I think we are good to go now. Now that we are convinced that from the experimental analysis we are making use of the t-test, we can then proceed and do the analysis. So this is the data for setosa, that is the sepal length for setosa. So we can go to analyze, scroll down to this compare means here, and choose one sample t-test. Okay, let's scroll down. Now let me clarify this before we proceed. I think in literature we are made to know that the t-test can only be used when the sample size, that's one of the assumptions, that the t-test can be used when the sample size is less than 30, right? But you have to know that a t distribution is also a symmetric distribution or it is a family of curves that is based on the concept of degrees of freedom, which is related to the sample size. Okay, so as the sample size increases, the t distribution approaches the standard normal distribution. So even if you have a sample size that is more than 30, you can still make use of the t test. Okay, in books, once the sample size is more than 30, we may tend to use the z test, right? But in here, even when the sample size is more than 30, we can still make use of the t-test because it is also a symmetric distribution. Okay, so let's maybe drop this inside this box. Okay, and the hypothesis value was 6, right? We wanted to find out if the average value of the sepalent is different from 6. So this is the conjectured or the hypothesized value, which is 6 centimeters. Okay, let's look at the options. Okay, we don't have much to do here, so we can click on OK to proceed. So click on OK. Let's go to the results window. Alright, so this is the information with regards to the t-test for the Ketosis variable. Now let's scroll down and see. Alright, so in here we have the mean value to be around 5 centimeters. I wanted to find out if this one is significantly different from this one or it is due to chance. Okay, if you look at this from the analysis, right, this is the statistic value and this is the p-value or the significance value for 2T test. I want to compare this to the threshold value of 1% or 5%. Okay, we only reject the null hypothesis if this one is less than the threshold value or the alpha level of significance. Because this one is less than it, right? You can say this one is almost 0, which is less than 1% or 5%. So we are going to reject the null hypothesis and conclude that the average value or the mean value of the sepal length for Ketosis is different from 6 centimeters, right? So that's the conclusion that we are going to make per the result that we have obtained. So I think we are good to go. Now we can do same for the vesicular data. So this is our vesicular data. So from the experimental analysis, we were convinced that the t-test was required. So let's go to analyze, compare means, and let's use the one sample t-test. Right, so let's drop this inside this box. That's the sample length. Right, and let's change the hypothesis value to 6. Test value to 6, yeah. So we can click on continue to see the result. Let's go to our result window. Okay, so from the average value from the sepal length for vesicular, we have around 5.9 centimeters, almost 6 centimeters. I want to find out if it is different from this or it is due to chance. Now if you compare this p-value or the significance value to the threshold value or the alpha level of significance of 0.05 or 0.01, it means that we are failing to reject the null hypothesis and conclude that the average value or the mean value of the sepal length for vesicular is not different from 6, and we can see that the mean value is 5.9, which is almost 6, so the difference is not all that much. That's why we are basically making this inference. Okay, now let's check that of the Virginica data. So I want to do the t-test for the Virginica data. So let's go to analyze and scroll down to compare means. Let's use the one sample t-test. Scroll down, let's drop this inside this box. Okay, alright, so the test value, let's change this to 6, right, and click on OK to basically view the results. So let's go to our result window. Okay, so we have this. The mean value for the sepal length, right, is 6.6 centimeters for Virginica, and we can see that we want to find out if this one is different from the hypothesized value or it is due to chance. Now the result from the t-test, the p-value is less than the threshold value of 1% or 5%, right? This one is less than the alpha level of 1%. So it means that we are going to reject the null hypothesis and conclude that there's enough evidence to indicate that the average or the mean value of the sepal length for Vesicular is different from 6 centimeters. Okay, so I think we are good to go now. So now, assuming the assumptions that we tested for failed, that's the normality assumption, always the data is continuous. We can see that's from what, if you look at the data, it's already continuous, right? So we can see that we don't have to basically worry ourselves with the continuity. But what we normally test for is the normality assumption. Now, assuming that the normality assumption failed, then we are supposed to resort to the nonparametric test and make use of the quantile or the sign test. Now, but before we make use of the sign test, we have to know that the sign test is used to test the value of a median for a specific sample. So the first thing that we're going to do is to basically generate a variable for median, right, where the data point is made up of the hypothesized value. So let's say we know the hypothesized value was 6, so I'll have to first of all generate a median value where the data point is made up of the hypothesized value, right? So this is a variable for median. I'm going to do it in a proper way. I'm just illustrating this, right, with an example. So then the next thing that we're going to do is basically is to compare, right? Once you have created a variable for median where the data point is made up of the conjectured or the hypothesized value or the median value, the next thing that we're going to do is to compare each of these data points with that of the hypothesized median, right? And if the data is below, if this one is below the median value, we are going to assign it with a minus value, or let's say a minus sign. And if it is greater than the median, we are going to assign it with a positive value or a positive sign, right? And if the data point is going to be the same as the median or the hypothesized median, then we are going to basically discard it or assign it with 0, so that the test statistic value for the sign test is going to be the smaller number of the plus or minus sign at the end of the day. Okay, so that's what we're going to do. So first of all, let me clear this one, clear this, and then let's go to transform. I want to create the variable for median, so I'm going to use a compute variable, right? And I'm going to say let's call this median var. That's a median variable, and I want each of the data point to consist of the hypothesized median value, right? So I'm going to make it 6 and then click on OK. Alright, so here we go. So I've created that. Let's look at the variable view. So let's scroll up. So you can see that the median value or the median variable is now numeric, right? Let's look at the measurement. It's nominal. So let's change this to scale. Okay, let's go back to our data view. Scroll up. Alright, so now that we have done this, let's go to analyze. Scroll down to nonparametric test and scroll down to related samples. Now we can use this. We have two ways we can do the sign test in SPSS. We can use the related samples approach, or we can scroll down to legacy dialog. And in legacy dialog, we can scroll down to the two related samples. So I'm going to use the first approach and later use the second method. Okay, so related samples. Alright, so let's scroll up and choose fields. I'm going to drop this variable inside this box and do same for the median variable that I created. Let's drop it also inside. Okay, once you have done that, click on settings. Let's check that of the customized test. Scroll to this side, compare median difference to the hypothesized. Let's check that of the sign test, right? Okay, and let's click on run to see the result. Okay, so here we are in our result window. It's still running. Once it's done, we are going to see the results. It's still processing. Okay, so here we go. So we can see that let me scroll down. So we can see in here that we have the significance value to be 0.000 there is a level of significance, the alpha level of significance. We are comparing this p-value to that of the alpha level of significance. Okay, now the decision is that we are going to reject the null hypothesis. You see that has been colored in some yellow orange color. So this is the decision that we are going to take. Because this one is less than that, the significance value is less than the threshold value of 0.05, we are rejecting the null hypothesis and conclude that there is enough evidence to indicate that the average or the median value of the sepal length for the setosa variable is different from 6 centimeters. Okay, let me go and use the second approach and see what conclusion I'm going to draw. You can see that this result is similar to the inference we made under the one sample t-test. Let me go back to the setosa data. Yes, so now I want to use the second approach. So analyze, scroll down to nonparametric test, legacy dialogues, right, and let me use this approach, the two related samples approach. Alright, so in here, the test pairs box, I'm going to drop this variable, sepal length, as one and the median var as the other one. Then I'm going to uncheck this and check that other sign, right? And let me see. So we can click on OK to see our results. Alright, so here we go. So if you look at this, we are interested in the p-value, which is 0.00. If you compare this to the alpha level of 0.01, it means that you are rejecting the null hypothesis and conclude that there's enough evidence to indicate that the median value of the sepal length for setosa is different from 6 centimeters. Okay, so these are the two ways you can actually apply the sign test in SPSS. Okay, now let's go back to the data for vesicular and do same. So assuming the assumption for normality failed, then we are going to resort to that of the nonparametric test. But first of all, we have to generate a variable of median, right, where each of the data point is made up of the conjectured or the hypothesized median. So let's do that. Transform compute variable. So I'm going to say median var, right, and I need the conjectured median, which is 6. Click on continue. Okay, so once we have created that, we can then proceed and go to, first of all, let's look at the variable view. I think we'll have it as nominal. Let's change it to scale. Yeah, so let's change the median var to scale, and then click on data view, go back to analyze nonparametric test. I'm going to use the first approach, which is the related samples, and click on fields. Right, let's scroll down. So I'm going to check this and drop it inside this test field box. Let's drop it. Right, and let's do same for the median var variable. Drop it inside. Right, so let's go back to settings and check the customized test. Right, and let's check that of the sign test and click on run to see our result. Okay, so what do we see in our result window? The p-value is 0.461. If you have to compare this to the significance level of 0.05 or the threshold value, it means that you are failing to reject. So if you look at the decision here, it says retain the null hypothesis, which means that you are failing to reject the null hypothesis and conclude that there's insufficient evidence. Okay, there's insufficient evidence to indicate that the median value of the sepal length for vesicular is different from 6 centimeters. Okay, now let's do same for the Virginica data. So let's go back to the data for Virginica. Okay, so assuming the assumption of normality failed, right, then we are supposed to resort a non-parametric test, but first of all, we have to generate a variable of median where each of the data point is made up of the hypothesized median. So let's go to transform compute variable, and let's make this median var, that's the name of the variable, and let's put the hypothesized median value of 6. Click on OK to proceed. Okay, so here we go. Let's go back to the variable view and let's change it from nominal to scale. Sorry, nominal to scale. Yeah, so now median var is now scale. Let's go back to data view, scroll up to analyze, nonparametric test, and related samples. Okay, so let's go to fields and let's drop this variable sepal length inside this box. Okay, and let's highlight on the median var and also drop that. Okay, so let's go to settings and let's check that of the customize test and check that of the sign test. Scroll down and click on run to proceed. Alright, so let's scroll down. So this is the result that we have. If you compare this p-value or significance value to the threshold value of 0.05, there's a decision that we have here is that reject the null hypothesis. So we are rejecting the null hypothesis, right, and conclude that there is enough evidence to indicate that the median value of the sepal length for Vesicular is different from 6 centimeters, right? So I think we are good to go now. So this is basically how to do a detailed analysis, right, for one sample data in SPSS. Please, if you find value in this video tutorial, don't forget to subscribe if you have not, and also turn on the notification bell to get updates anytime I post on this channel. Thank you for watching.